Robotics is perhaps the most anticipated technology of the 20th century, while it's finally delivering on that science fiction promise of truly useful, general-purpose humanoid machines. Speed, mobility, dexterity, vision, and the user interface are all progressing so rapidly that hardly a week goes by without a major advancement. Engineers, however, must deliver on that promise, and they know that the essence of motion is power. And in robotic applications, particularly humanoids, the need to use batteries or onboard fuel cells to operate systems makes physics the limiting factor in ultimate machine performance. Converting the energy available for the onboard power source into forms that drive the mechatronics and the logic is a serious matter for robot designers. And joining me now is an expert on this subject. He's John Quinlan, Senior Engineering Manager for Murata Power Solutions. John, it's this subject, it couldn't be more timely. Everyone is talking about it. It's all over the media. Every place we're seeing the latest iteration of humanoid robots in particular, but mobile robots in general. And of course, compared to sort of the industrial robotics world that I remember, you can't just jack these things into the mains. Basically, you're carrying your power with you. So this implies that we've got different voltage levels, different current demands, basically, but only a single source of power.
Absolutely. Yeah, it's very critical. Humanoid robots are typically powered by lithium-ion batteries, and that's typically a 48-volt system, which is somewhat derived from the telecoms industry and standards that we're used to. However, there's a lot of stress placed on that lithium-ion battery in terms of transients, back EMF, noise, and this is all generated from the inductive loads used on the humanoid robots. So it's critical that the DC to DC converter that connects to that lithium-ion battery is robust enough to cope with those extreme transients that we see.
Yeah. Now, I'd love to loop back to issues like the back EMF and the signal issues at this point, but can we talk a little bit about the DC to DC converter? Historically, of course, if you wanted to convert something other than, say, a simple voltage doubler, you basically converted to AC, ran it through a transformer, and then rectified it. How does the technology work when you go with a solid-state DC to DC converter?
Yeah, so we're using switch mode power conversion. We take that DC voltage, we filter it, we suppress the transient from that, and then we switch that at a frequency through an isolation transformer, and then the output is rectified, smooth, and regulated to a usable low voltage DC level.
Yeah. Now, it's interesting as we think of it in this day and age, we think of things like audio or RF world, and there's a digital world where basically the signal's either there or it's not. And so you can tolerate a fairly dirty signal in a way. But back in the day, of course, the RF or the audio people, they would think about high band pass, low band pass filters, LC type circuit. How do you filter a dirty signal if you've got issues like this in a power system like this?
Well, we utilize the latest passive component technology. We fine-tune our filtering on board with the DC-DC converter, and we're typically getting less than 1% ripple peak to peak on the output. So it's a very stable, clean DC source that we're supplying to the customer for use.
Now, intuitively, of course, we think of battery systems in particular. Fuel cells might be a different matter, but with batteries, we always envision that the power is ripple-free and super pure. That's flatline voltage. Is that in fact the case?
Absolutely not. No, I mean, from a lithium-ion battery, first of all, you've got the regulation of that voltage, as it starts to decay, as we take power from the battery. So you have a voltage range to tolerate, and typically with a 48-volt system, that could be as low as 35 volts, could be as high as 60 volts, steady state operation. On top of that, you've got those additional transients. So we typically have to cater for 100-volt transients on that 48-volt bus. And we're seeing now the limitations of that 48-volt lithium-ion battery. To increase efficiency of the system, that voltage needs to increase. So now we're seeing typically 60 volts, 72 volts, up to 100 volts of that battery, which reduces I squared R losses within the system, enables a longer run time and more efficiency.
Yeah, it's interesting you mentioned it. Fascinating how, Ohm's law rears its head no matter what you do. And in the automotive industry where I come from, in the 1950s, systems went from 6 volts to 12 volts because of the increasing sort of current demand and the increasing complexity of the electrical systems. Then it stayed at 12 volts in internal combustion technology to this day. And for the last 30 years, many players have been trying to adopt a 48 volt architecture, aware of the fact that, increasing demand is a factor. Now, of course, we have electric vehicles, so all bets are off. You can basically design the architecture any way you want. But for those who are not necessarily electrical engineers technically, can you describe why we want a higher voltage compared to a low voltage high current system?
Yeah, so with a higher voltage, the load, the resistance, if you like, will stay the same, but the current will increase. So a lower voltage on the battery results in higher current. Higher current requires heavier copper, heavier wire gauges, and that increases cost, size, and you're going to have a resistance effect across that wiring loom because of that. If you increase the voltage, the current reduces, and therefore we can reduce wire gauge, copper, and have a lower voltage drop.
Yeah, and I can see how in a mobile robot, or especially a humanoid, where every gram you can save from the weight is going to pay off from the physics.
Absolutely, which results in longer run times, which is critical for these machines.
Yeah. Now, of course, if we go to higher and higher voltages, I start to think about the dielectric strength of the insulators around the conductors as well. At this point, is there any issue with flashover if you have like tight bundles of very, very small conductors?
Absolutely, yeah. The safety extra low voltage standard is 60 volts. So if you go over 60 volts within your system, you then have to comply with international safety standards. And part of that requisite is that we have to have an isolation barrier between input, the battery, and the output, the source load. That isolation barrier is critical. Should any fault occur on the primary side or the secondary side, you're going to be physically isolated from that energy source. And the isolation barrier is typically 2,250 volts DC, so that you're ensured that no matter what happens, you're going to have a very safe system and voltage to work with.
Yeah. Now, that's an interesting issue from that safety perspective. In some of the consumer goods industries that I've worked in, a standard quality check before the product was packaged we called a high pot test, high potential test, where, of course, then we check the dielectric strength. However, if we could simply ground the chassis, if we want to create a current path to sort of get some of that current over there, or we could put a crowbar circuit in to pop a fuse, or some sort of a ground fault circuit breaking system built into the thing. These sort of standard of safety systems. But a humanoid robot's a different story. That's something which actually is not connected to the mains. There's no ground path which you can drive that stray current. So how do you handle that? Are we talking about double or triple insulation, or just high tech insulators in the conductors?
Yeah, I mean, the isolation levels are set out with the international safety standards. And for operating, for example, at 100 volts DC, the isolation barrier value is quite low. However, we actually use the maximum value, which is 3,000 volts AC, 2250 DC, to just make sure that no matter what the conditions are with the temperature, humidity, moisture levels, dirt ingress, nothing is going to get across that voltage barrier.
Yeah, yeah. Now we keep throwing around the concept of high voltage or higher voltage. What are the levels? What's it in a typical DC application in, say, a humanoid robot? How high are the voltages?
So we're seeing the ever increasing voltage battery level as I described earlier, and now we're approaching 100, 110 volts DC levels. That enables much more efficient system and longer life within the robot, which means that we have to have this safety dielectric strength across the primary and secondary of that power conversion stage.
And how high are the levels, say, at the actuator, at the user end of the product?
So the voltage levels are typically either 12, 24, or interestingly, we're now proposing 48 volt DC architecture. So customers that already have that 48 volt power system architecture in place, they can use a higher lithium ion battery pack, but convert that to an isolated, clean 48 volt DC voltage. So they can still utilize the architecture in the system, the actuators, the motors, everything that runs off 48 volts. They don't have to change that to work at 100 volts, for example. We provide that regulated DC to DC converter stage to make a 48 volt system that then can be used.
Okay, so the designer in me, immediately when I hear this, I'm thinking that how do I design my system? Do I design it from the actuators back or design it from the battery forward?
Well, battery forward is the best way, of course. However, with constant iterations of existing designs that are running off of 48 volts, the workload to do that could take many years. So to simplify that effect, system architectures are typically using the 48 volt systems they already have and converting that high voltage battery voltage to 48 volts. And, there's a lot of components, as you mentioned, the automotive industry now running off of 48 volts, typical sensors, components, communication modules are all geared up to run off of 48 volts, not the 100 volts today.
Yeah. Now, of course, I mentioned I'd like to loop back to the cleanliness of signal because, of course, that's that every designer that's a factor. In automotive wiring harnesses, in my experience, we used to lament that everything is an antenna. Everything, every conductor in the vehicle is an antenna, and that has implications. Is the same thing true with humanoid robotics? Because I'm assuming that the wiring harnesses in these things are wildly complex, and there's an awful lot of copper in there just trying to pick up some stray RF anywhere I can find it.
Absolutely. EMI is fundamental in any system and more so in humanoid robots. The signal cables, the power cables, your sense cables, for example, are all typically bunched together, grouped together, and it's critical that you don't get any cross coupling, that you manage your earth strategy, the system that you designed to suppress noise is all done in a clear and concise manner.
Yeah, you mentioned the Earth. How do you ground a humanoid robot? Because you don't have the ability to just basically drive a copper stake into the Earth. I mean, do you simply establish sort of a zero datum at a floating voltage level?
Yeah, so typically it would be similar to e-mobility applications. So the chassis is actually 0 volt grounded. So the secondary side, we have a 0 volt, and the chassis system will be connected to that 0 volt so that all noise sources can be coupled to that level.
Yeah, yeah. Now you mentioned back EMF, and that lit me up immediately because I'm thinking, of course, in the automotive world where so many actuators are solenoid driven, essentially, is that once you cut the power, you've got to deal with that back EMF. And for small actuators, of course, we just throw a diode in there and we just dump the power. Do you use a strategy like that with robotics these days?
Yeah, so we're actually investigating now how we can utilize that excess energy from when an inductive motor actuator switches off, that extra energy that's delivered from that inductive load. How can we use that? So we're now investigating bidirectional converters. So let's say we have a 48 to 12 volt DC-DC converter. And the 12 volt side, as soon as it sees that burst, that surge of voltage come through, it will actually bidirection and switch that energy back to the 48 volt cell. Something that we're paying very close attention to.
That's an interesting concept, a bit like regenerative braking. You mean to take that waste energy and push it back to the battery?
Absolutely. Yeah, absolutely. Yeah. And with these systems running on batteries, if we can gain an extra 10% of run life, it's worth doing.
Well, that's a provocative and fascinating concept. So if a robot, for example, is lifting heavy objects, could it use some of that gravitational potential energy as the weight drops to sort of feed power back into the system, theoretically?
Yeah, so we're actually relying upon the motor switching on and off. So as a limb moves, lifts a heavy object, there's a lot of torque there, a lot of current being delivered. As soon as that actuator motor stops, we got to then dissipate that excess energy. And one of the ways we do that is to send it back to the battery pack to replenish the charge.
Yeah. Now it's we're talking, of course, about humanoids because it's hot, but this may apply to mobile robotics in general. Is that for standard fixed base industrial robotics, mass is not really that big a concern because in some ways a heavy solid base is not a bad thing. So you can push a lot of electronics down to the part that doesn't move. In humanoid robotics, everything moves. So you still have that inertial mass that pops up, whether it's at the end of a hand, an end effector, or whether it's moving the entire thing. And batteries are heavy; they're damned heavy. So if you can't do anything to optimize battery mass, it's very difficult to make batteries lighter than what they are. Is the pressure on to make all the rest of the componentry lighter?
100%, yeah. Light and efficient are the key attributes here. So in terms of designing the DC-DC converter, we're using wide band gap devices, typically gallium nitride, and we're switching the frequencies even higher so that we can reduce the size of that DC-DC converter and make it more efficient. And one of the critical aspects is mass. As this humanoid robot is moving around, you get a lot of inertia, shock, vibration. So reducing that weight, it reduces strain on the overall system.
Sure. I can see how it could ripple through the system. You mentioned gallium nitride, the advanced semiconductors, wide band gap. Of course, the power people have been very enthusiastic about these new semiconductor materials. It's the enemy in my world, in the world of a lot of people in these industries, is heat. And in my world, of course, it was simply a matter of, that's fine, I can use an aluminum extrusion as a heat sink, I'll put in a fan and I'll blow air through the cabinet basically, and I'll just reject that heat to ambient, it's no problem. Humanoids are a different story.
Absolutely. And it's, a common attribute that every 10 degrees C increase in component temperature reduces the life of that system by half. So 10 degrees C is huge. So how do we reduce that heat? Well, we're using gallium nitride, which has a very low RDS on from drain to source. It has a very low gate capacitance, overall capacitance charge, which allows us to switch that device faster from those losses. So we're able to achieve efficiency levels from a few years ago of 92% typically. We're now at 98% using wide band gap devices.
98%? In a semiconductor device running at 98%?
Absolutely, yeah, correct.
All right, that's shocking. That's a good transformer design would attempt to achieve something like that.
That's right, and that's our Achilles heel right now is the magnetics. What do we work on next there? So
yeah. Wow, that's impressive. All right, so if that suggests that heat is manageable, at least on that DC to DC converter side.
Yeah. So what for this application? Of course, there's no liquid cooling. There's no giant fans to take that heat away. So we utilize the chassis within the robot. There are additional heat sinks, especially around the processor board. And what we do is we have a base plate or a conduction cool path from the DC-DC converter that can take that heat away to a cold wall surface, which some customers choose to have a low airflow fan. Some customers have conduction cooling only, convection, no fans. So we're able to take that heat away and dissipate it around the system.
Now, that from an engineering perspective, I can see how there would be a tremendous advantage that way because cooling is a serious challenge for many electronic systems. Cold plates, if you're looking at liquid cooling systems, the computer people have to deal with this problem all the time. The data centers, that's a serious problem.
Absolutely. And with static applications to typically data centers, especially in the world of AI now, we've reached the limits of forced air cooling, what pressure we can apply there. So now we're looking at other techniques, liquid cooling, direct liquid cooling, taking the heat away from that DC-DC converter via fluids, and even immersion cooling.
Now, you mentioned static in the different sense meaning of that word, but since you brought it up at this point, what about ESD? What about mobile robotics at this point? Again, it's not a matter of you can't just drive a copper rod into the ground to dissipate static charge.
Absolutely. ESD levels can reach enormous strengths with the robot walking around the factory. We have to apply a very solid grounding technique. We have to ensure that the DC-DC converter can withstand those high industrial levels of ESD. And we do that by passive filtering within the device. Is a very critical subject area, ESD, within mobile applications.
Yeah, yeah. John, just to give us a sense of the scale of these things, what's the form factor? What would the physical size and mass typically be of a DC-DC converter used in a humanoid robotic application?
Yeah, so typically we'd start off with industrial standard form factors. So we have what we call a half brick design here, and the device is PCB mounted with the top side having a conduction cooled base plate area. This is half brick industry standard. Then we move down to what we call a quarter brick level, so slightly smaller. Again, industry standard footprint that many industries and customers utilize these form factors. And then we go down to eighth brick. And then we get down to 16th brick. So we're reducing the size all the while. And particularly the smallest brick here, we've got the 16th brick package. Customers love this, but they're limited by how much power you can get out of it. However, with the latest wide band gap technology, we're able to push power levels in this, what we used to be able to get in the half brick. So industry standard packages, PCB mounting, the ability to conduction cool and take that heat away are very important factors for customers.
John, would these be attached to the board using surface mount technology? Would it be through hole? Would you use a socket to make it replaceable? How would you mount it?
Yeah, typically through hole, soldered, and that's due to the high currents that we're generating here for the main power blocks. For a smaller power, particularly for limbs, fingers, the power is much lower there. So we would typically deploy silicon architecture, which is IC type power conversion devices. Especially using our proprietary charge pump technology from our sister company, P Semi.
Now, of course, we're talking about a very, very very space-constrained application here. So it's not as if you can have a sprawling motherboard and just essentially, as you say, solder this thing straight down to it. How convoluted is the packaging in this case? Could this be expected to be inside a sandwich board? Would it potentially be potted in a different system?
Yeah, so different areas of the humanoid robot have their own power spaces. So if we take about the most power hungry section, which is the processor board, typically using a Thor processor, for example, which is a mini motherboard, the DC to DC converter would be directly mounted onto that motherboard. So we take the 48 volt noisy voltage from the lithium-ion battery, and we convert a regulated, clean, isolated 12-volt source that motherboard can be powered from. That motherboard is then typically cold wall mounted to an alu substrate or an alu design within the body of the humanoid. And the heat is dissipated not only from the DC-DC, but from the processor board as well.
Sure. How about reliability? We have to talk about it. Inevitably, it's a factor down here. How do you measure reliability in humanoid robotic applications? Is it mean time between failures? Is it number of power on, power off, or charge cycles?
Yeah, so we have two methods to calculate that. We have a mean time between failure, which is a calculated assessment of the components the temperature, the environment that the DC-DC is used in. And we also have demonstrated, so real life data of failures. But to reduce that failure rate, we employ techniques such as potting of the DC-DC converter, so that not only does that allow the heat to conduct freely to the conduction cooled surface, but also provides a shock and vibration element to that DC-DC. As you can imagine, these robots are moving fast. There's a lot of force on the limbs, and a lot of shock comes through the system. So shock and vibe is critical to the life expectancy of electronics packages within that system. And we qualified all of our products extensively internally to IPC standards, so shock, vibe, temperature, humidity, all these good things from an environmental perspective. And we also qualify from an electrical perspective. So we will typically put the converters in a Holt chamber, and we will run the converters electrically whilst inducing those environmental factors to the device.
It almost sounds like an aerospace environment.
Absolutely. E-mobility, commercial off-the-shelf products, they all kind of adhere to the similar standards in terms of requirements for reliability for that system. And humanoid robots is with no exception. Shock, vibration, moisture, temperature range, dust and oil ingress. As you can imagine, a lot of these devices are used in factories. They're moving, they're picking up objects. So ingress is a key factor to suppress within the humanoid robots.
Yeah. John, how does a design engineer specify the product? Is this a catalog thing, or is it a matter of that they have a power need, they encounter that, and they pick the phone up and call and say, I have a problem here, please fix it?
Yeah, so there's two areas there. So we like to design what we call broad market offerings, so that one device will hopefully fit all. And with careful communications, marketing strategy with these customers, we're able to get feedback about what the requirements are that they need, not only from an electrical perspective, but from other factors such as communications, shock, vibration, operating temperatures. And we're able to design a product that one device fits all. However, there are instances where something doesn't exist off the shelf, and we will work very closely with the customer and design a unique bespoke converter for them.
John, you've shown me some very, very small form factor units, surprisingly small in form factors. Project forward 50, 60 years, if you had 30 years at that minute, is that as this technology evolves, we're now getting into advanced semiconductors. You mentioned wide band gap, superconductivity. The temperatures are starting to approach room temperature. In the future, will the DC to DC converter exist in the form it is now, or are we looking at something radically different, do you think?
It's a great question, Jim. It's a very good question. And it makes me excited to talk about this, because where are we today? So we've achieved efficiencies of 98%, which is super high for high power DC-DC converters. We're almost hitting the plateau, the limit of what more we can do efficiency. So what's next? So how do we minimize that footprint, increase the power, and dissipate that heat? So there's a number of techniques that are being closely monitored, engaged with, and that is packaging, heat dissipation. They're the two most important factors of how we move forward with DC-DC converter technology. In high power systems, we're looking at liquid cooling within the PCB substrate. Can we take heat out there efficiently, which reduces the size? Packaging of the device is fundamental in how we manage thermal flow from the heat dissipation within that converter. They're the two main factors that I believe are going to be key attributes for the future of power conversion design.
What a fascinating future. John Quinlan, Murata Power Solutions, thanks for joining me on the program.
Thank you very much, Jim.
And thank you for watching. See you next time.